Yeah, so the title of this talk is Erlang Engine Tuning, but that's sort of a major title for a number of talks, and we're not going to see much tuning today either. It's just the third talk in the series, but if you come to Stockholm this summer, I think we'll get to some tuning parts actually in the next talk in this series. So today I'm going to talk about the scheduler, but I'm going to talk a bit more high level and give you a couple of war stories, actually. So imagine that you have a company that does some kind of online transaction processing, and you're dealing with lots and lots of money, and you have to handle transactions not extremely fast, but within a certain time. In the case of Klarna, where I used to work, we actually had 15 seconds to handle a transaction. And that sounds like a huge amount of time in the kind of transactions that we're talking about in the other talks here today with billions of transactions per second. But our transactions were a bit more heavy. It basically, from no information at all given by the transaction coming in, we have to make a credit decision and decide whether we trusted this person or this IP address that came into our system to actually give them credit for actually sometimes very large amount of money. And this we had to do within 15 seconds, and we usually do it within 100 milliseconds. So we had built this system, and we started with just being able to serve a few and scale the system. And at this point, about a year and a half ago, we handled many, many transactions. And everything was really nice and calm, and the system was working fine. And then one night, bam, one of the nodes just went down. And then a long search started for where did that slave go. So it turned out that when you don't have much work to do, like on a calm night like this one, the Erlang schedulers actually go to sleep. So if they don't have anything to do, they go to sleep, and actually several of them go to sleep. And you might end up with just one scheduler running. And the last poor scheduler then tried to do term to binary. So we're using Nisia, the fantastic database built into the language. And Nisia has different types of tables, but one type of the tables it keeps in ERTS tables, and every now and then it dumps the whole table to disk. So it writes a log to disk of changes, but every now and then it decides, just to be on the safe side, if we need to do a restart, we want to do it quick, we write the whole table to disk. Now in our case, we had big tables, and we had tables with big entries in them. So we had entries, one-line entries that were like 600 megabytes or something like this. And then it had to write a number of rows that each was 600 megabytes. So it tried to do a term to binary in a 600 megabyte line of code, line of data. And it turns out that term to binary takes what's called reductions. We're going to come to that. Takes 20 reductions. It doesn't matter how big term you have. It's 20 reductions. And it's just going to run until it's finished. So what happened was that this scheduler was running, and then it went into dumping the table, and it did a lot of term to binary, and it didn't use any reductions, so it never got scheduled out. The same process got to run for over a minute. And you know what happens then? That's my wife going for the kill. Heart goes to kill you. So we're monitoring our system with heart. So if they become unresponsive, we kill them and they restart. Very nice thing if a restart is quick, but in our case, a restart is 1.5 hours because we have these big tables that need to be reloaded. So this was not really a good design, but in the beginning, it was very nice that Heart restarted the system, but at this point, Heart was actually the killer of the system. So it could probably have survived by just dumping this Nisia term and doing it for a long time, and then finally finish, and everything would have picked up. But since there was only one scheduler running, only one process running, there were no one answering Heart's pings. So then Heart decided, this node is dead, I will kill it for real, and just brought it down. Took some time to find that bug. It was quite an easy fix, then we just bumped the reductions in each iteration in Nisia. We'll get to that in a short while. So about a year later, we didn't have this really nice and calm night anymore, but we had a constant problem of our transactions timing out all the time. And then we decided to upgrade to R15 because newer is better, you know. And R15, there was only one thing that changed in the bytecode, and that was that there was one new instruction called line. So this gives you line numbers in error messages. What could possibly go wrong? Well, something could possibly go wrong. So we had this system running, and we had it on R14. We upgraded to R15 in a running system, of course. That's what you do when you run Erlang. And then after a week, we recompiled all the code and got that up to R15 and got the new line instructions in. And then, then we had problems. Then everything was timing out all the time, basically. As soon as there was any load on the system, it just went down, didn't do anything. So it turned out that we had this bright young programmer at some point that designed an API where you did a throw outside of the API. And of course, no one on the outside of the API knew what to do with the throw that came from inside the thing. So that thing just flew around a bit until it came to a top-level catch that saw, here's a throw that I don't know what to do. Let me do a stack trace on that one so we get a nice error message with line numbers. And those stack traces were quite big, but also they happened 60,000 times per second because this pattern was just not handled and all the time. So suddenly we had 60,000 get stack traces per second that tried to, for each element in the stack, tried to find a line number for that element in the stack. And guess what? How many reductions do you think this cost? Nothing. Get stack trace, that doesn't cost anything. So any server or any scheduler running a process that did get stack trace, didn't use any reductions, and could just keep on doing this. And all our transactions were throwing these exceptions all the time. Yeah, so not a good thing. Just not doing the stack trace in that place just fixed everything. But it was not that easy to find that bug either. Okay, that was the introduction. So both those problems were actually huge problems in our code base, but one part of the problem was also how the scheduler in Erlang works. So this talk is about the Erlang runtime system. Oh, how much time do I have? When did we start? I have no idea.
We're about 5 minutes late.
Till half past. Okay. So the Erlang runtime system, we can look at it as a number of components. So we have the Beam interpreter. The last talk that I gave in Stockholm was on the Beam interpreter. You should have been there, but you missed it. There's the garbage collector. I gave a talk about that here in San Francisco last year, and some problems that you can end up with binaries and how memory is handled in the Beam. And there's other components like Hype, the native code compiler, and how I/O is handled that I'm going to talk about later. And then processes is such a central concept, so I'm going to talk a little bit about processes today and in every talk, basically. And then we're going to concentrate on the scheduler. So processes, conceptually, it's just 4 memory areas and a pointer. You have the stack, the heap, a mailbox where you get your messages, the process control block, and then there's the PID that actually points to this process. So if we look at the Erlang runtime system as memory areas instead, laid out in memory, we have the runtime system code, the C code. We have the C stack, which the emulator and the runtime system is running on. We have lots of queues. We have separate area for binaries. And we have processes. And then we have loaded Beam code. So processes for us now is just memory. It's the process control block, the message queue. And then I lied a bit. So there's not a stack and a heap because they are one memory area growing together. But if you're running Hype and native code, there's another native stack instead. So there's still 4 memory areas. And in the process control block, you have all the values that control a process, like a pointer to the top of the heap, the top of the stack, and where the heap ends and the stack ends, and continuation pointer to see where you're going to keep on running next time and so on. And then there are a couple of fields that are important for the scheduler. So there's fcalls, which is the number of function calls that you are allowed to run until you have to yield. There's the reds, which is the total number of reductions that you have done. I'm going to talk a little bit more about what the reduction is soon. So these two keep track of that. You have the status that says if you're running or waiting or whatever you're doing. You have next and previous pointer where you can point to other processes when you're in some kind of queue, which you basically are all the time. And then you have a priority. And then there's lots and lots of more fields in this block. So let's go back to the components and look a little bit at Beam then. So I'm classifying Beam nowadays as a garbage collecting, reduction counting, non-preemptive, directly threaded register virtual machine. And I'm saying non-preemptive here. So usually you have preemptive multitasking or cooperative multitasking. So that's the 2 things that you can choose from usually. So the Beam, let's talk about Erlang and Erlang processes first. Erlang processes are preemptive. So conceptually, as a programmer, you don't have to think about when you yield a process. So if some other process needs to run it will get to run at some point, and your process will yield at some point. In the beam, this is actually implemented in C, and C is not preemptive. So the beam has to implement this preemption on the processes. So it does this with something called reduction counting. So the scheduler is non-preemptive and reduction counting. So what is a reduction? Well, nobody knows, but basically it's a short amount of work done by a process. So every function call is counted as a reduction. So when you enter a new function, beam checks, have I used up all the reductions that were available for this process? Yes, then it will have to yield. Otherwise, it keeps on running. And since there are no loop constructs in Erlang, the only way you can create a loop is by doing a tail call. This is actually a function call, and this function call will be seen as a reduction count and check for whether you need to yield or not. Of course, there's other ways a process can yield. If you do a receive and you have no messages in your inbox that matches, or if you call some certain BIFs that needs to trap out and do some other work, or a special actual yielding BIF. But the main thing is reduction counting, and the whole system for the scheduler is built on that reductions should always be used for any a small amount of work in the process. So then we come to the main topic of the talk, the scheduler. So first, in a multi-core system, you have to realize that there's actually one scheduler per core. This is not set in stone, but if you don't change any parameters when you start up your system and you're running a multi-core system, then you get one scheduler per core. And each scheduler is actually a thread in C, and they run in parallel. So if you have a 4-core system, you have 4 schedulers, and you can run 4 processes in parallel. If you have more processes than that, they will sit in queues waiting to get to execute. And these queues are per scheduler. Yes, so now we're going to look at the process state machines, reduction a little bit more in detail, how the queues are handled, and timing wheels, and then we'll come to some possible problems with this. So this is the process state machine. A process can be running, it can be waiting, runnable, suspended, exiting, free, or garbage collecting. So when a scheduler is running a process, it's obviously running. Also, when a process is doing garbage collection, this is done in the same process. It's in the same scheduler. It goes into the garbage collecting state, does garbage collection, comes back and keep on running. Then when a process dies, it ends up in a state exiting, and it cannot go away completely directly because there might be dependencies on memory areas that cannot be freed at once. So there's a few steps before it actually disappears, a process, when it dies. And then there's a suspended state that I just put there to get a lot of arrows in there to confuse you a bit. We're not going to talk about it. You can suspend the process, and then you can get it to resume But notice that if it's running and you suspend it, it will not resume as running. It will end up in some queue somewhere. But the interesting parts are the running, getting a receive, going to waiting, ending up in runnable, do a schedule or a yield. So in running, we're counting reductions, function calls, also BIF calls. So here, BIF calls are getting better and better with every release to actually count a number of reductions that is closer to the amount of work they're doing. But in the beginning, it was usually like append, that's heavy, that's 20 reductions. And other BIFs is just one reduction and so on. So nowadays, they actually, most of them give a good number of reductions that are reduced each time. The garbage collector uses a number of reduction proportional to the amount of garbage it has handled. So it gives a good amount estimate of the time that it's been using. So when you get to 0 reductions, you yield and go to the runnable state. If you do a BIF trap or you get a busy port, you also end up in the runnable state. The process can actually keep on running still, but it's not allowed to. But if you do a receive and you have no matching messages in the inbox, then you go down to the waiting state. So if you end up in the runnable state, there are actually 3 queues for processes on each scheduler, and they are for the priorities of the process. So we have max priority processes with its queue of processes, high priority processes, and then you have normal and low in the same. But each time you find a low priority process, you just increase a counter, and I think it's 7 or 8 times that it will ignore. I just think it will ignore it 7 times and run it on the 8th, but I'm not sure. So you ignore a low priority process the first times you see it, and only pick normal processes. And this queue is just, whoa, a first and a last pointer in a queue structure. So the first pointer points to a process, to a, actually it's just a PCB of the process. And in that PCB, there's a next field, as we saw earlier. And this next field will be used to point to the next process in queue, and to the next one, and then there's a null terminator at the end. And then there's a last pointer to the last element in the queue. So this is just a simple, ordinary queue where you add things at the end and pick them out at the top. And very easy, both of these operations. Since you have the last pointer, you just add it here. When you add something, and when you pick it out from the top. So as long as there are max priority tasks, those will be run, then the high priority, and then normal. And there's also port tasks, which are things that need to be run on ports. And these are run in each iteration of the scheduler loop. We'll come to that in a short while. So there's basically 4 queues of things to be done in the scheduler. Oh, now we can actually see what it says. And then if a process goes into sleep, it goes into the waiting state. And in the waiting state, if you have a timeout on the process, you say receive after 1000, then do something. Then you end up in this timing wheel. So the timing wheel is just a big array, and you have a current time. It says this is the time slot that we're at right now. And when you put something into the timing wheel, you calculate what slot in the timing wheel it should end up in. So if it's going to be 20 milliseconds later, I'm not 100% sure about what the granularity of each slice is, but let's say 10 milliseconds. So if it's 20 milliseconds later, you end up in a slot 2 slots away. And if it's 65,536 times 10 milliseconds plus 10, then you will end up in that slot, but on the next iteration of the timing wheel. So the array is just one array, but you can see it as a wheel that just goes on and on. And in the data structure that's stored there, you also keep track on what level of the wheel you're at. So if you have wrapped it around a couple of times, you get a higher number there. And then when time is advanced and it checks whether something has timed out, it goes through all the slots that has passed since it last time checked, moves this pointer forward, and for every timer that is on level 0, it will wake them up and put them in a runnable queue instead. And timers are not only just processes. You can, it's actually a separate data structure, and there are a couple of things that can create timers. Yep. So adding things to this wheel will require a lock, but in practice, I haven't seen that that's a problem. So one problem with this scheme where we have processes of different priorities is that if you add lots and lots of processes of a high priority or a max priority, you might get priority inversion, or if you add a lot of processes with a low priority. But you shouldn't be worried about this, and you don't even really need to know about this. And just don't mess with priorities, and nothing bad will happen to you. So there's a C function called schedule in rlprocess.c. So how many of you have watched Luca's scheduler presentation, the webinar that were a couple of, okay, a few of you, yes. So Lucas, who's sitting here, he said it's quite short and not hard to understand if you know C. Yeah, it's 560 lines of if-def C code. It's I wish I had the minds of the people working at the OTP. That's all I can say. So I haven't really understood this thing yet. So I had to steal whatever Lucas said in his presentation, basically, change it a little bit so no one noticed. So it's actually not schedulers that call the emulator to run Erlang code. But what's happened is that the emulator starts up and is running in beam emu.c, and then it called process main, And if you want to see big C functions, you can look at that one. And then when a process needs to yield and it needs to find a new process to run, then it calls schedule. And schedule basically does a number of things. First, it updates the reduction counters. And this sounds like a simple thing. It's one reduction counter. No, there's like 7 variables that get updated with this reduction count in different views of it. And then it checks whether any timers in the timing wheel has triggered. And then if this particular scheduler has been running for 4 million reductions since last time an IO check was done, or a balance check was done, then it will do a balance check. And we'll come a little bit to what a balance check is. But basically, it prepares how process will migrate. And in the next step, and this step is done every time in this loop, it will use the information from the last time someone did a balance and actually have a set of migrations to do, just follow a plan and move one process from one scheduler to another, or a port. And then it will do some internal work, free up memory or handle code loading and things like this. And then there's a global variable. So this function calls variable is global to all schedulers. So when this one goes above 4,000 reductions, then it will check for IO and update the time. So it will try to not update the time unless it needs to. But if you have 2 schedulers and you run 2 schedulers and they get to run for 2,000 reductions, that means that every time both of them have run for 2,000 reductions, one of them, or the total has been 4,000 reductions. So actually, for every 2,000 reductions, you will do a check IO in time, so to speak. But this is to keep it from the way it was when you had only one scheduler. You did 4,000 reductions amount of work before you checked the check for IO. And you do the same amount of work, but you do it in less time. You do it as the time divided of the number of schedulers you have. So this is actually done quite often. And then it will execute a port. And if it sees that it's not getting the finish with the port, it will actually execute many port tasks for 2,000 reductions. And then when it returns, it will actually have found out which process to schedule next and return that process back to the emulator, which then actually runs Erlang code. So every 4 million reductions, there's the load balancing code. And if you want to see scary, hard to understand C code, go no further. This is fantastic code. I hope that I will decipher it and put something in the book that I'm writing that can explain what's done, but don't bet on it. I'll talk to Rikard and people, but we'll see. So basically, the plan is to move processes to lower number schedulers. So as long as a scheduler is not overloaded, you want to move as many processes as possible to it so that you run as few schedulers as possible. Mostly to get data locality, but also you could reduce CPU usage if you want to. I'm not sure anyone tries to use that, but possibly done in some projects. But basically, if you get things running on one process, you get more data locality, and things might work better. But if you see that some scheduler is overloaded, it will start moving away processes from that scheduler. Now, as we saw earlier, if you're using BIFs or even worse, NIFs that are not counting the number of reductions in the right way, then you might end up with starvation because you might have just one scheduler running all your processes, and then that scheduler is doing a lot of work for very few reductions. And then we get to the bad places. So there's a solution nowadays. You can add plus SFWI plus a number of milliseconds, like 500 or 50 or whatever you want, to actually wake up sleeping schedulers. So if you use this flag, there is a separate thread that monitors things, and if it sees that schedulers are sleeping, but there's actually work to be done, it will wake that scheduler up, and then that scheduler will start stealing work from the other process. So what happens when you go down to one scheduler is that there's no, and that scheduler is locked into work, there's no other scheduler to actually start stealing work from that scheduler. So with that flag, you get a more stable system in this way. Yeah, so there's a number of problems with the reduction count mechanism. So BIFs uses an arbitrary amount of reductions. A return doesn't use any reductions. And NIFs uses an arbitrary amount of reductions. So BIF uses an arbitrary amount of reductions. Should you be worried? Yes. Do you need to know about this? Yes. And what can you do? Well, fix the BIF. Yay! That's the way to go. Help out, please. So if you can't do that, you have to use small data sets. And there's a function called Erlang bump reductions. So if you know that you're doing a BIF call that's actually using more resources than it's going to account for, you can do a bump reductions with some number afterwards. So for example, if you do term to binary in earlier version of Erlang before it was fixed, then you can do a bump reductions with the size of the binary, for example, afterwards, and then you get the number that's more in line with what's actually happened. So you can actually see this. Nowadays with a nice function called Erlang system monitor, which now takes a long schedule argument. So you can monitor for long schedule things, and then you give the number of milliseconds that you think is long. So in this case, I said 10. So if one schedule run takes more than 10 seconds, we will get a monitor event. So what? If we, for example, call list sequence with a huge number, it turns out that it goes into something that takes a long time, and we get a long schedule event. So if we do it for reasonable numbers, it's not a problem, but if you do it for a bigger number. And also, as I said, function calls are counted as reductions, but returns are not. So we have this late return function here, which just counts down to 0. And it does this not tail recursively, but recursively. And on its way back, it adds 1 to the thing. So this is not a function call. This will be inline operation in the beam. and it will not count as a reduction. So if you do call long schedule with a big number, it will actually not count reductions, and you will get a long schedule on this.
The problem is not the returns. The problem is the inline BIF.
The plus inline BIF?
Yes.
Possibly, but you could probably make something else that just returns for a long time. So return does not use, should you be worried? No. Do you need to know about it? Probably not. Use tail recursion and don't have insanely long call chains. And this you do normally, so it's not a problem.
How big is insane?
Well, in that case, what was it, 4 million? And I think that was sort of the border in my case for the 10 milliseconds thing to trigger. NIFs. Should you be worried? Yes. Do you need to know about it? Yes. What can you do? Don't use NIFs, please. If you use NIFs, make sure that they can yield sometime in the NIF and that they're using reductions in accordance with the amount of work they do, or wait for dirty schedulers that are supposed to come in R17, and then, yay, all is fine again. Okay, so there's usually one scheduler per core. You have several prioritized run queues. Preemption is done by reduction counting. It's not perfect. And the load balancer will try to minimize the number of active schedulers. So that can be good or in some cases bad. Questions? Yes.
Have you had a chance to play with the dirty schedulers at all?
Have I had a chance to play with the dirty schedulers at all? No. Yes?
Can you make this easier for a Ruby programmer? Oh, wait, this is the wrong one. You talked about receive zero and yield. If you can go back to that slide, they went two different pathways. If you did a yield, it went back to running, but receive went to waiting when there's no messages in the message queue. But if I do a receive zero and there's no messages in the message queue, does it stay in the running state? Continue immediately, or?
Yes, it's, then it should be runnable.
So the difference between yield and receive
Or it shouldn't
zero,
even go out there, I think.
the receive zero with no messages in the message queue will just keep running, whereas yield will send you out of that state.
Yes, I'm confused now, but I'm sure you're right. Yeah. So if you're not actually having a timeout, but you have zero, then it doesn't. I don't think it even goes to the scheduler. It just keeps on running in the beam. Pretty sure about it, but
That's what I wanted to verify. That's what it was.
yes, you can easily look at the source code and verify that.
I had trouble bringing it up with my Ruby editor.
Okay. Yes.
I was interested that you said that the timing wheel didn't have much of an impact on performance, given that's going to be in almost every Gen server call with a timeout on it. Isn't that going to become a scaling point?
So it's first of all, it's hard for them to actually end up in the same slot. Usually, it's a big timing wheel. You have 65,000 of them. But of course, there's the lock on the timing wheel. So, actually adding things to the timing wheel, and it can become a problem. But I haven't seen it myself. But and I tried to stress it, but I didn't manage to do it. But theoretically, it should be a problem. So if you can come up with an example, I would be happy to see.
We have like benchmark we've done that shows that there's problems. And like one of the patches that was WhatsApp version of the DB that actually fixes the blocks did improve it. So there's also a separate block which we didn't talk about, but also there's the block for the BIF send timer, and that is also a different block.
Yes. So there's a nice feature now that you can do the lock profiling. And if you recompile your runtime system with lock profiling on, and then run your benchmarks or your test suites or whatever, you will get many interesting results. So very nice tool that I hope to be able to present more about in a later talk. Yes?
How does the asynchronous threads schedulers, how are they handled in terms of reductions? I mean, you have the regular process schedulers, right? And then you get the -8, actually the class A asynchronous threads that do I/O or I don't know, driver async calls.
Yes. So how are asynchronous threads handled with regards to reductions?
Yeah.
So they're not. So they are just C processes running, doing their work. And for each asynchronous thread, you have actually an asynchronous thread that is running on the side, and it's not affecting all the other schedulers.
Like you can't block the VM or you can't block the VM, right?
In-
You can't block the VM version of
No, no, unless there's a bug in something that's done in them.
with work that doesn't yield. I mean, if there's like a type could be there, it doesn't block the rest of the yield.
No, it's not supposed to do that.
Yeah, but
So I think we have time for one more question, if there is. No? So let's thank the speaker.